Hello everyone, and thank you for attending today's webinar, Network Modernization with Source Packet Routing, sponsored by Juniper, with participation from Bell Canada and Microsoft. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you today, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. Finally, an on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I'd now like to turn the event over to Principal Analyst in Optical Networking and Transport a Heavy Reading, Sterling Perrin. Sterling?
Hi, thank you, Hannah, and good morning and good afternoon, everybody. Welcome again to Network Modernization with Source Packet Routing, sponsored today by Juniper, and we do have a great kind of a special webinar today. We have 2 invited speakers, so let me just introduce the speakers here briefly, and then you'll hear from them as we go through the course of the next hour. So I'll be the moderator. I'll just very briefly introduce the topic so we can move on to the main agenda of speakers. We'll hear first from Aman Kapoor. He's Director of Routing Applications with Juniper Networks. And then we'll move to our invited speakers. We'll hear from Paul Mattis, Senior Network Software Development Engineer. He's with Microsoft. And then Dan Voyer, who's a Technical Fellow with Bell Canada. So really looking forward to the user perspectives as we go through the course of this. You should see in front of you right now a look at the agenda. As I mentioned, my role will be fairly brief. I'll take that first point on the agenda, segment routing in Spring, just setting some definitions. And then Aman will take over from there. He'll talk about market drivers and trends and looking at an overview of the source packet routing technology as well as use cases. And then we'll move to our service providers, first from Bell Canada. And then after he presents, hearing from Paul from Microsoft, and then Aman will wrap up. This will be, as you can see, a fair amount of speakers, but we will hold 5 to 10 minutes for Q&A at the end, and we'll actually be able to run a little bit past the hour. So please do ask away as the questions come to you, and we'll get to as many as we can. So in terms of Spring, the topic, source packet routing and networking. Just a bit on some of the definitions before we dig in. So segment routing and source routing are 2 terms you'll hear, and they're essentially synonymous terms to describe a very specific type of routing packets through the network. In source routing, an ordered list of instructions is applied to an MPLS label at the source node. So that's the source in the naming. The label stack provides all the instructions that are needed to get the packet through its destination. So if you look at the simple diagram on the right, you can see R1, router 1 is the source node, and it has a label stack there of 3 labels in this case, and that's the information that gets it to R6 on the other end. That's the destination router. Just a couple points on this. In this case, you can see 3 labels. Obviously, it's a simple diagram, but the fact is it's not unusual in a real-world network to just have a very simple list of labels to get from source to destination. We've seen multiple studies that show that the vast majority of destinations can be reached with just 2 or even 1 label being applied. So it really is simple in that sense. The other key point on simplicity is because all the information is coded at that source node, there's no requirement for those intermediate nodes along the route, as many as there are, to maintain network state. And that's really one of the other keys to the simplicity compared to other types of traffic engineering, and probably most specifically RSV, P, T. So our speakers are going to provide a lot of details on the mechanics as well as the use cases. The very last point I'll make is the IETF standard version of segment routing is SPRING, source packet routing in networks. And so it is being standardized. There's some 50 RFCs in various stages right now of completion. And I've listed just one of them here, RFC 7855 is an informational RFC if you want to just start digging in to get more information. But there's quite a few. And the standardization is important, and I believe a very large reason why there's so much service provider activity ramping up, particularly in 2018, which is what we'll get to. So with that very brief introduction on definitions, let me bring in Aman to talk through some more specifics. So Aman, I'll hand it over to you right now.
Thank you, Sterling. Good morning, good afternoon, everyone. This is Aman Kapoor. We have a pretty packed agenda, so let's dive right into it. I wanted to kind of touch base on level set on what we're seeing in the industry, where we're heading, and then kind of build from there how Spring or source packet routing enables us in the direction that we want to head towards. So we're seeing a pretty seismic shift in the networking industry, and this is being fueled by an exponential growth in devices, so 5G adoption and IoT. With that, about 31 billion devices by the end of 2018. And it's not just devices, they're connected devices. So that is the key word, which means that they are putting a lot of diverse requirements on how these devices need to be connected, what applications are driving these changes. So some of the applications that we are all familiar with, connected cars or driverless cars being a pretty popular one. Outside of that, medical applications, industrial applications. So a lot of these applications bring in with them different kinds of SLAs that they want from the network. And with the devices and the sheer growth, the traffic itself, the internet traffic is growing tremendously. So it's expected that the global internet traffic will grow threefold in the next 5 years. And it's not just the growth, the traffic patterns are shifting themselves. We're seeing that mobile traffic or smartphone traffic percentage will be much higher than the conventional PC traffic. Machine-to-machine traffic will increase at a much higher percentage. And CDNs will carry over 70% of traffic moving forward, which means there'll be a massive east-west replication that needs to happen for these CDNs to be refreshed and make sure that they are current. So all these are putting a tremendous amount of requirements onto the network. In essence, applications, as people write applications and they are global, they want the network to be invisible. Now, for that to happen, the network needs to be modernized. It needs to react to the application needs. And so for an application perspective, it's invisible, but to do that, it's a lot of work that needs to happen to get there, to get where a network can be invisible. So because of this, the service providers are also actually looking to see how they can provide services and turn on services really fast. So as I'm sure there are a lot of service providers in the audience, you very well know that it takes a long time to turn on a service. Then reaction to growth is slower when it comes to putting in more resources. And conventionally, the services have been hosted on the physical devices itself. So to get to the demand and to take care of the demand, it's important that the service infrastructure becomes more agile. And as part of that, service providers are looking into virtualizing a lot of these network functions so that they can increase at a much higher rate and keep up with the growth. And Dan from Bell, he'll talk a little bit more on the Bell's use case on how they are achieving it. So with this, there are changes and there are requirements being put on the network. The existing set of requirements that we are all familiar with, which is scale and performance and resiliency, still hold true. In fact, with the new architectures of scale out versus scale up, the actual control plane scale is increasing at a rapid rate. To be able to quickly turn on a service, as I mentioned, the network needs to be highly programmable, highly simple, and easy to manage as more and more of such virtualized network functions come up. So for that, the requirements are not just increasing, but they're also diversifying for the end goal of network being invisible and reactive to the application needs. So this topic today will deep dive into how Spring is enabling us to modernize the IP MPLS infrastructure. Before we get there, let me just give you a quick primer, and Sterling touched briefly on it. So as he mentioned, Spring or source packet routing is based on Spring or segment routing is based on a premise source routing paradigm, and it's not a new paradigm. It's been there and it's revived, and it kind of gels well with the new set of requirements that we talked about. There are two key building blocks when it comes to Spring. The traffic is steered through the network using a series of instructions, and they're called a segment. A segment actually can represent it represents an instruction. It can be topological or it can be service-based. Segments are encoded. If it's V4 MPLS, they're encoded as MPLS labels, in which case the forwarding infrastructure is compatible to the existing MPLS switching and MPLS forwarding infrastructure. Or they can be encoded as an IPv6 address. In that case, the encoding is done in the IPv6 extension header. The forwarding is based on the active segment. So let's take the case where it's V4 or MPLS, and in case of that, the active segment would be the top of stack. The forwarding will be based on top of stack. Now, the ingress or the edge can steer the traffic with by pushing a series of such MPLS labels that are identifying the instructions. And this makes the intermediate nodes not have to maintain any state, which makes segment routing or Spring inherently scalable. The other neat features that Spring brings into the picture is our ECMP. It's very natural and natural ECMP in Spring. And as I talked about in my previous slide, with the scale-out infrastructure, ECMP becomes a very critical requirement. So let's dive a little bit deeper into traffic engineering using Spring. So there are two components of traffic engineering. First is how do I actually program a path onto the ingress routers? And there are various ways that are available for that to happen. Initially, when Spring was forming up and ITF just started with standardizing Spring, the natural extension was to enable RC3107, which is BGP LU, to now carry a stack of labels. But that was kind of limiting because it doesn't give you capabilities like weighted ECMP. And for that, a new address family was introduced, which is called BGP SRTE. Now, that address family gives you a possibility to create a policy to an endpoint, and then the policy is actually identified by a combination of an endpoint and color, which means that if you have two policies towards an endpoint, one policy can represent a high bandwidth path, the other policy can represent a low latency path to the same endpoint. And depending on your application needs, you can pick policy A versus policy B. And there are extensions happening, similar extensions happening to PCEP and NetConfiang. Or if you look at the OpenConfig config project, they're coming up with a new programmable mechanism called gRibeye. Now, how do I steer traffic into this transport is actually done using there are various mechanisms provided for that. You can have firewall filters, you can do class-based forwarding, or you can actually do an explicit policy. Before I hand over to Dan, let me quickly go over where things are and what people are looking. So in the IHS study, it was shown that about 10% of the operators have some form of Spring deployed into their network, and by the end of 2019, we're expecting about 60% of operators will have some use case being solved by Spring. So if I were to classify really high where Spring or segment routing use cases come into, these I will classify them as the first being shortest path routing, so you just eliminate any label distribution protocol from your network and can just use IGP to carry the actual SID information, do a complete fast reroute, do some level of very lightweight traffic engineering or traffic steering, and then you actually move to more heavier use cases like fully traffic engineered path and interdomain TE. So for the ones on the left, you really actually do not need a controller to actually form a path and push it, but a controller would be good to visualize how your traffic is flowing. But in the latter case, it's required to have a centralized controller do the job of path computation and actually pushing it. And if I were to describe the big verticals, service providers are kind of all over into their spectrum, but majority of them are looking right now at shortest path routing and solving the FRR problem. As Paul will talk about, the cloud providers already had RSVP in their network, and they're looking much beyond those use cases. So with that, I'll hand to Dan.
Thank you, Aman. Good morning and good afternoon, everyone. This is Dan Voyer from Bell. So we started our journey in about a few years ago under the project name that we called Network 3.0. And back then, and still today, the problems that we were tackling are the following. So as everybody noticed, and this is coming from our own tools, the internet traffic is growing in an exponential way. And then you can see on the top right here the traffic that we were noticing about a year ago. On the bottom left, this is the routing table scale that, as expressed by Aman, is still growing in an exponential way. When you combine the two together, then you have a very good use case for disaggregation of network component. Maybe you want to look at keeping the data plane in the hardware, but moving the control plane in the software, which means we will have to introduce some or turn our CO into a more DC style, and I'm going to talk about that in a few moments. And also for us, since our asset is really the backbone and the network infrastructure is our main asset, it is very hard to move and innovate at the speed that we're seeing from those graphs. So that requires a lot of planning and a lot of time to push and insert new protocols and new features. So we have to think about that in a new type of architecture. Other problems that we're tackling is, this is a graph from our tools about how messy and meshy it looks in operators network. And it's it's very difficult to do and deal with all the endpoints from a traffic engineering perspective. So we know with the traffic growth, it's not just about having big pipes. We have a use case, or we need to better manage our own network in a more efficient way, in a cheaper and a faster way. So you could see over the last couple of decades, traffic engineering is quite complex. It takes us a long time to plan and insert new endpoints. And even if we do that, it's always been very complex to deal with traffic engineering, like RSVP and stuff like that. So the fact that we have states in the network also makes it a little bit hard to move with the migrations and so on. We also had few to little OEM tools to monitor our traffic through the tunnels, as you could see here. So this trigger for a new type of architecture. And with that comes some next generation requirements. So we were looking for a more standardized and open standards from the industry. We're also looking for a more programmable network architecture and have features to be enforced in software and hardware at the same time. We wanted to, whatever we do, we wanted to have a transition from the brownfield to the end state, so evolve at the pace as we will be able to bring new features. By doing so, in our case, we just picked an island in our network that we used as a green field to introduce new features with in mind that it has to be interoperable with the brownfield, and that's how we will. And we are actually using our own infrastructure to bring segment routing gradually and smooth at the same time. We wanted to be able to have some explicit path computations. And as a lesson learned, and what we've been dealing with that is really start from a greenfield to introduce the new stuff, and then have in mind that it has to interrupt with the brownfield at the same time. And I'm going to touch that a little bit later. So this is a very high-level view of a typical network operator. What you can see here is the access where on both sides of the access you have your consumer and enterprise. The metro or the aggregation network is where we aggregate all the access. IP core is where we have most of our IP routing traffic coming in and offer the door to the internet. So a CE, for example, will sit on the other side of the access. The PE will be on the boundary between the IP core and the metro. And then the first use case that was very, very easy for us was to bring segment routing straight in the IP core to get some benefits from fast reroute, as already mentioned. Part of our transformation, we wanted to go straight to RCO and turn them into CODC. We refer that as CORD for Central Office Redesign Network. What you see here is two levels of DCs. However, with the rise of 5G, we're going to be adding more of those COs in DC. Things like edge computing would be located somewhere in the access and even closer to the users. Now, in the different COs, the main one is where we're going to have most of the orchestration piece of it, VNFs and CNF for containers. Cache engine will be located around the tier 2s, internet cache or CDN for videos, cache closer to the user as well. Now in here, over the last almost like 30 years, we've been adding a bunch of routing protocols and technologies that makes it very hard to make it automate and programmable. So we came up with some of the guidelines. We want to be able to simplify our network to a set of key protocols that you can see here in the middle. And then we want to be able to standardize in order to automate what we've been doing from the network protocol side. The orchestration is also another piece that is very important. As we distribute different CODCs, we're going to end up with a lot of those. We need to centralize the orchestration and the provisioning towards those COs by a main piece that we refer as the orchestration. And this will enable us to simplify the provisioning, to enable us to automate on queue protocols, will allow repairs, almost self-healing, will be able to integrate with new technologies such as the 5Gs, like the slicing, or coming with that will be required with the 5Gs, the IoT, a bunch of other use cases that will be benefited from that. And we want to be able to do this in a seamless way and try to limit, almost remove all the state from the network and use overlays instead. Now, when we're looking at this, we're thinking of, this is our way of expressing what I've expressed so far, is we're looking at the network could be handled by itself with a new type of protocols like TLFA and node protection, microloop avoidance, or traffic engineering, where the network can self-heal by itself and not have an orchestrator to go and code every single piece in the network by it directly. The self-management piece of it on the left side is by bringing the SD-WAN, the ONAP, or the end-to-end network orchestration, be able to have a better control on the FIB, do on-demand path. Those are the examples that we're thinking, and it's kind of a 50-50. You don't want to put everything in the orchestration. You'd like to have some, and make the orchestration some kind of a gut box. And if you look at the RFC at the bottom, you'll see that we're pretty much aiming over that direction. Now, as we turn our first CO into DC, this is an example of how we did that. So we started with a closed network in our COs where you have the torus leaf and spine and the border leaf. We are interacting directly with the core network without any specific DCI mechanism. This is directly from ISIS segment routing all the way to the top of rack. We are also integrating with the metro network, and you could see the type of use cases that we're tackling here, like the VCE, the VPE, the voice app, the virtual rendezvous point, or the virtual route effectors. Those are the components that comes from the core. The control plane use cases are the easiest actually to virtualize and tackle. This allows us a lot of flexibility. So we're relying on equal class multipath with segment routing. We have added the fast reroute in the fabric to be able to answer the requirement from voice and videos, and also make the support even better. By doing so, we are looking at self-repair when you have those fast reroute mechanism in place in the network without having to have extensive or very complex control plane mechanism. It's differ from the CODC classic DCI. In our case, the CODC sits in the middle of the network, so you could see the access are coming from the metro or directly to the leaves at the bottom left. The traffic enters from the access in the fabric and then leaves towards the core. So the CODC is really in the middle. So we wanted to have something seamless without any handoff. One key, and here you could see one of the typical use cases. So it's crystal clear what we're trying to do here is a virtual PE or a leaf could act as a PE, will interact directly with the PE in the field. We wanted to make sure that the brown field, green field interoperable works seamless. So in this picture, you could imagine the PE still be in the LDP with OSPF as an IGP, for example, interacting with the leaf as a PE, which is a segment routed device. The same thing with the VPE on the left side, where the VPE establish a L3 VPN connection directly to a brownfield PE. And this is done with some main component. So the mapping server is really the key component for a better and a good interaction between the brownfield and the greenfield, where the greenfield in this case is the SR MPLS domain that you see at the bottom. This is required for the migration and will remain up until we finish migrating over ISIS and segment routing. That will take us a few years to get there because of there's so much devices in the network. There's different type of versions. There's a lot of upgrades to be done and performed. But at least we get the benefits from the get-go, which is also help us to have some learnings and lesson learned right away and not wait that we convert the entire thing one shot, like a ship in the night. We wanted to have a progressive integration into the network. Now, we've been conducting a lot of tests about fast reroute. This is a sample from our lab where we had very good convergence time for a lot of scenarios. In this case, we see a scenario where we have a local failure between two nodes, where you see the red cross there. And we're roughly around 20 millisecond convergence time for a lot of, like, close to 10,000 routes in this case. Remote failure as well as microloop is also things that we're looking at, and we have very good results. And this is done, once it's in place, the fast reroute is very simple to put in place, as well as the microloop. We're talking about few line of command, and then we have a fast reroute end-to-end on every node across the backbone, which is very helpful for our service assurance. Now, with segment routing comes a lot of things to plan. For example, the segment routing ID, how you're going to distribute the label across every node. In our case, we came up with different type of service. This is an algorithm. This is an example how we do things here at Bell. We have the sRGB base. We're talking about 65K of SR MPLS labels possible. The base will be 16,000, but in here you see different type of service, like you want to be able to address your infrastructure underlay. Maybe you have a different service like IPVPN and or Internet. And we embed how we are able to have dedicated or unique SR label to make sure that we don't have any conflict. So the calculation is done with the loopback of every node in this case. And a very good example is on the next slide in here with some configuration on the Juniper devices. We have an absolute label that's calculated from the loopback that you see on the top here. And then we have also the index at the bottom where we see 12,584. That's the index, and on top, the 28,000 is the absolute value. Now, once you have your algorithm set, this is not something you want to do manual. So we just coded and then embed the different range of the different services into the code to make sure that we always get a unique set of SID and assigned by the loopback. So in here, I have embedded a piece of script from one of our top programmer based on Python, where we have a loopback address, and then we embed a prefix SID here, and then why not adding the net ID from an ISIS perspective. And in here, you could see on the left the different set or the different step to get to make sure that we don't have either a duplicate IP or either a duplicate SID. So by pooling the entire network and centralizing the configuration and and have it centralized around a database, and we use things like an open daylight, but we could also use North Star. There's plenty of application where we could sync up with what's in the field. Then you do like an A/B testing with the IP database and make sure that the IP is never being reused once it's pushed into the network. And then we do a commit check before we push into the network, and then we commit directly into the infrastructure. And that's how we are able to make sure we don't have either a duplicate IP or a duplicate SID in the network. This makes it has to be very easy to provision the infrastructure without creating any mistakes. Now, this is very much our view of where we're going. We want to be able to bring segment routing all the way to the host where we will host VNFs. We want to be able to steer traffic and add features like service launching chaining, or have a predicted path from the host on the left over the host to the right. And at the same time, if there is a failure or there is a link overloaded in the middle of the network, we're going to steer the traffic to a different direction in the network to make sure that we respect the criteria such as latency and bandwidth per application. We call it application responsive networking. So with that, I will pass it to Paul Matz. So Paul, it's all yours.
Thank you very much. Good morning and good afternoon, everyone. I will be talking about Microsoft's use of Spring in SWAN, which is our interdata center network. I have to start out with a disclaimer slide, which is that this does not constitute a commitment by Microsoft to use any particular technology. This is a work in progress, and some of the details may well change before it actually happens. Given those warnings, though, this is definitely more than slideware. So the problem being addressed here is Microsoft's interdata center network. And we have, I'll try to speak up then. Microsoft has a number of networks. One of the largest ones is the one that connects the data centers together. The important points about that network is that we have very high data volumes, and those data volumes are growing also at a very high rate. It's characterized by elephant flows, so those are large, long-lived streams, generally for data replication. The network is geographically diverse, which means that there are big differences in latency over different lengths. So making the wrong decision to cross the ocean or not can have grave consequences. We have multiple SLAs for our internal customers that we need to maintain. That the network is very expensive to deploy and to run, and having that network be unreliable is not an option. So the solution for that is SWAN, which is SDN for the wide area network. I have a link here to the original Microsoft research paper. SWAN, as deployed right now, largely matches what's in that paper, although we have evolved it over time and improved it quite a bit. And the very, very highest level components of SWAN are traffic engineering pipeline, and then we run proprietary agents on each of the routers inside the network. We use an MPLS data plane with a traditional single label pushed at ingress, swapped at each transit node. The entire path across the network is programmed by a central controller that's part of the pipeline. We do class-based forwarding. sending best effort traffic over lower latency paths and scavenger traffic split over lower and higher latency paths. And scavenger also has a lower drop priority. If you look at the existing architecture, the lightest blue box in the middle there is the brain, that is the centralized traffic engineering engine. We collect, we have IBGP sessions with each of the routers to figure out what prefixes live where, so we can figure out what traffic needs steering. We push the routes out through a controller. There's a lot of detail here that isn't really germane to the Spring discussion, so I will leave that as an exercise to go into more detail if needed later. And there are some current issues with this architecture. First is proprietary agents running on each of the routers. So if we wish to go to a different vendor, we need to port to that architecture. We need to maintain a fork of our code, and environments for running agents on routers are generally unique. We also have some route scaling problems that are associated with programming the entire path centrally and steering each prefix separately. And we have the delay and synchronization problem that we can't steer traffic into a tunnel until the tunnel has been signaled end to end. So what we are doing is to evolve that solution using the existing SWAN controller and then changing our programming and steering method to use Spring. What Spring gives us is vendor independence. We have verified everything that we need works on Junipers and on Cisco's and on Arista's. We're using standard protocols to set up the basic infrastructure and connectivity using ISIS. We only need to program the edge of the network. We will use a standard protocol, BGP-TE, to program the tunnels and steer traffic. There is no need to synchronize tunnel setup, and it minimizes the state kept in the network and the amount of state change that has to go through the network. More cool stuff. BGP-TE policy is defined per next hop, not per destination prefix, so there are many fewer routes. We use IGP shortest path routing as a fallback if the TE pipeline fails. So if we fail to push out a traffic engineering solution, traffic will still flow. We get to take advantage of fast local repair with TI-LFA. For monitoring purposes, we have the ability to probe individual members of bundled interfaces. And it gives us a path to future integration with other Spring-based technology. So at a very high level, the diagram gets quite a bit simpler. So basically, we get topology information from the network and generate a solution on a schedule, and we push that out to a new service called the BGP conduit that uses BGP-TE to set up the tunnels and steer the traffic. So the pieces and parts of the new solution, the SDN pipeline re-optimizes the network on a 2-minute cadence. And the components there, high-level components, are the traffic engineering engine, which produces a Spring-specific fib. Flow collector, which gathers S-flow samples from the routers to figure out where the traffic is coming from and going to. Bandwidth predictor, which aggregates those flows together and applies machine learning to predict traffic patterns for the near future. We also have a bandwidth brokering system, which is our admission control, which is for explicitly throttling the elephant flows. Then there is the BGP conduit, which is a service that is basically a programmable BGP route generator. The fib is pushed to the conduit, and the conduit turns that into BGP-TE policy updates. And we use per flow steering, so we can do class-based forwarding. We program WCMP paths, and we use explicit labels. The conduit also performs tunnel OAM, so we are also continuously probing the health of each tunnel, and if for some reason a tunnel is unusable, we will take that, we will reduce the weight of that tunnel to 0, so we'll stop using it. So this is the dynamic piece in between the periodic reoptimizations. Then there is our topology service. We use BGP-LS, and that's how we learn what how the controller learns what the labels are and learns what the changes to the topology are and what the available bandwidth is on each of the links. We also have to deal with traffic that we don't want to engineer. For example, BGP sessions, network monitoring information, and anycast traffic we do not engineer. And we handle that by allocating a secondary loopback address per router. The unengineered traffic uses the primary loopback, and engineered traffic uses the secondary loopback, which is set by route policy. So as we learn routes from eBGP from the outside, we mark those as going to the secondary loopback. And that's what allows us to engineer it. Then there's tunnel OAM, again, that we do explicitly. So in between traffic engineering optimizations, we need to detect when tunnels go down in case local repair fails. And there is no general vendor-independent solution, so we rolled our own. We send probe packets at sub-second intervals, and when it fails OAM, as I already mentioned, we set the segment list weight down to 0, so that segment list is no longer used. And the OAM data path is a simple self-ping MPLS packet. So we GRE tunnel from the conduit to the ingress router. What's under the GRE header is the MPLS label stack of the tunnel we're probing, and then under all that is a UDP packet that goes back to the conduit. And the interesting limitation that we ran into immediately was label stack depth limits, where the limits are both in the number of labels you can push at ingress and the number of labels that you can see past when you're on a transit router to generate entropy for WCMP and for lag. The first cut to get around that is to know what that limit is on the network and to simply prune paths that won't work within that limitation. What that might lead to, so far has not, is suboptimal TE solutions. So we might not be able to optimize quite as well as we'd like. The second cut, which we hope we don't need to do, is to use binding segments. So we would program a path to the maximum depth that gets you halfway across the network to a binding SID that then replaces that last label with the remaining label stack. It reduces the benefits of Spring by forcing us to program and coordinate the programming of the transit nodes. So we are hoping not to need to do that. And that's all I have, and I will turn that back to Aman.
Thanks, Paul, and thanks, Dan, for the insight into how you guys are evolving your networks and how you're using Spring in that process. So everyone probably heard the use cases that both Dan and Paul are looking at in their respective companies, and some of the things that as they migrate from the existing networks into to use Spring, some of the things that are either being is a challenge that needs to be solved, or that needs to just to be aware as you embark on that journey yourself. So for that, the first one, and this was the last slide that Paul talked about, was the label stack depth. The label stack depth it determines how precisely you can actually steer a packet and how precisely you can determine the path. And also, if you were to do entropy, and if you have entropy, you have a requirement to do entropy, that requires labels to be added to the label stack as well. this, again, as Paul highlighted, needs the platforms to support not only the ability to push a deeper label stack, but also to be able to hash. And with Juniper, with our ASIC families on the MX5G series, it's a programmable ASIC, so it has a very flexible label stack depth and that we can push, and also the hash depth. We are qualifying a depth of 16. We have a beta code available, and we'll be prioritizing it at the end of the year. For our Paradise-based family, which is used in the PTX and the QFX 10K series, this is a fixed pipeline chipset. We will have a label stack depth of 8 and hash of 8. In fact, the hash here works a little differently in the sense that it uses bottom 8 labels up to 12. So let's say if you have a label stack depth of 12, the hash will be based on the bottom 8 labels, and actually you can also include the IP payload. So you can hash fairly deeply into the packet to do entropy, and one way of, because you can do that, you can potentially avoid adding more entropy label on ELIs, and just because entropy by itself is an unsolved problem when it comes to Spring. There are drafts, but it still remains unsolved. The second thing is, as you move the intelligence outside and into a central entity, for that central entity to make a decision and program that decision, it needs a lot of telemetry information from the network for it to make any meaningful analysis and actually come up with a label stack, with a path that it can push into the ingress routers. So there are a whole bunch of statistics that needs to be pushed out. Generally, operators have used SNMP for getting such things, but in such a real-time environment, such a dynamic environment, SNMP is pretty much a no-go from day one. So we've been streaming a whole bunch of statistics out from the line cards itself at a very, very high granularity and at a very fast rate. And that is more of a push model, and as a controller can subscribe to the events and statistics that it really deems fit and make use of that. So that whole model of pull in SNMP is now changed to push. And continuing on the controller, it is always a build versus buy decision. As Paul mentioned, Microsoft has their own controller, but I'm assuming not everyone has either the software metal that Microsoft has or the need to actually go and invest in building their own controller. So for that, Juniper, our North Star product, will be our Spring or segment routing controller. And it is not just Spring controller, it's also RSVP controller, so you can actually run your network simultaneously, which I'll talk in the next couple of slides. So for that controller, we are exporting the topology, we're exporting the statistics that I talked to in the previous slide for North Star to actually compute the ideal path and program it onto the network. So Dan alluded this in his talk on how do I migrate from my existing network into and introduce Spring into the network. And most of the networks out there are going to be brownfield deployments. There are very few greenfield deployments in certain use cases where that will be the case. So if you have an LDP-based network, there is a facility to actually use, there's a draft that talks about how do you map your existing network, which is LDP-based, to and interact with a Spring-based network. Now, how this can imply is, let's say you're building a separate domain, maybe you're building a new metro, and you're using Spring, but it needs to talk to your backbone, which may be still running LDP. So the edges need to map LDP to Spring and vice versa. Or let's say you're upgrading your backbone to migrate to Spring, and not all the devices in your network are capable of doing Spring. And yes, there is a plan to decommission them and upgrade those devices, but that's a long-term plan. So again, in that case, you would need something like this and to seamlessly actually operate in a mixed environment. And the services, it's very crucial that the services are not either or. That is, the services, there shouldn't be a requirement that all the services need to run on Spring or all the services need to run on LDP. It needs to be based on per service. So for a certain set of services, you may choose LDP, or a certain set of services, you may choose Spring-based transport. Similarly, if you have an RSVP network, and depending on your timeline on how your migration path is, it could be if you think you can migrate from in the next 3 to 4 months, which may lead to a different decision going in how do you migrate it, versus if you have to coexist for the next foreseeable future in like few years, then there'll be a different decision. And with RSVP, things get a little more complicated in case you're using RSVP with bandwidth reservations. And the problem here is Spring traffic doesn't see RSVP traffic when it's doing path computation and vice versa. Or actually, RSVP traffic doesn't see Spring traffic, and RSVP being greedy will try to reserve bandwidth even though there is Spring traffic on the link. So what we've come up with is a very innovative solution where you can actually throttle your RSVP traffic if there is Spring traffic present into the network, and your RSVP can seamlessly then either try to realign the path based on the requirements that it needs to do. So what is the vision here? So the vision here is to use these models and what I talked about, the telemetry, the software-driven control, to actually move to a self-driving network. And for that to happen, all these pieces need to come together. Further adding to that will be, how do I describe my intent, and how do I translate that intent to actual policy that can be installed onto the network. But all these pieces are being built and will feed into that vision that Juniper has, is to actually enable our customers to build a self-driving network that can be managed automatically with as little human intervention as possible. So just to close, we have put an emulation, and we have put a Spring SANDBOX from Juniper in. We partnered with TESUTO, and TESUTO is a network emulation platform. So we have put our Spring SANDBOX on there for you to play. So if you go on to tesuto.com/juniper-spring, you can actually go and use your topology to see how things will work. We have 2 demos there, again, that I talked about. How would you migrate for your existing network, which is LDP-based, to Spring, or how would you migrate your existing RSVP network based to Spring? You can go and play and see how that will work for you before you actually go and embark on that journey. So with that, I'll close, and I'll hand over to Sterling for moderating the Q&As.
Okay, great. Yeah, thank you. Thanks to all of our presenters today. Very good discussion, great overview, and it's good to get the use cases as well. We are at the top of the hour, but we've got, I think maybe we can squeeze in 2 questions. And before I do that, just one last reminder I forgot to mention up front. There is a companion white paper with this webinar project, so everybody who's attending and actually who's registered will receive a copy of the white paper, heavy reading authored white paper, which has some additional detail. With that, there was a question regarding Dan's portion, the Bell Canada portion. Maybe you could answer, are your PCE and orchestration components off the shelf or developed in-house? Hopefully you can get some insights there, Dan.
Yeah, thanks, Sterling. So we're looking at North Star with Juniper. We also are involved a lot in contributing and building around ONAP as the main orchestration. You can go see online onap.org for the orchestration piece of it. There's a lot of module around ONAP. And for North Star, for the PCE, we have a few running in the lab.
Okay, excellent. Thank you. Question for Paul on the Microsoft. You had talked about BGP TE, BGP with traffic engineering, and the question is, any specific reasons for BGP TE as opposed to using PCEP? Maybe some insights on that decision, Paul.
The reason was existing infrastructure and experience with BGP in general, a really good C# library for implementing BGP that was easy to add BGP TE to. And if we wanted to use PCEP, we would have had to start over from scratch with a new protocol. So it was the easiest path for us.
Okay. Yeah, actually there was a question came in for Aman, but it's a bit chopped up. I don't know if you could. That person could try to re-ask. Perhaps we could get at it. Well, this one here, we could try. I believe it's for Aman. Well, for anyone, it says routing protocol simplification, deploying segment routing, and getting rid of LDP and RSVP TE. What are the alternatives for multicast L3 VPNs? And it kind of chopped up from there. Anybody able to address that at all?
So I can take that, and Dan, if you want to
Sure.
provide your view, you're welcome to do that too. So you're correct. In the initial drafts of Spring in the IETF did not talk about multicast, but there are certain use cases that are being now asked in terms and developed in terms of how do we solve the multicast problem. There are a few options out there that we are looking at. One being using an ingress replication-like model to carry multicast traffic, and based on what your use case is, that may or may not be the best one for you. The other one, which is referred to as tree-sit, which can actually you can actually go and program the algorithm on each replication node in the network to build that multicast tree from the source to the receivers. Again, that entails the provisioning from the controller onto the replication nodes in the network, which again may or may not be applicable to what your multicast use case is. And the last one, which is not really entirely Spring, but in a similar vein, is what is called BIER, the Bit Index Explicit Replication, which talks about how do we extract the state of the network and put it in the packet the same way as we do with Spring. So that is something analogous way of solving the multicast case. Dan, you want to add something?
No,
maybe if you've got anything, yeah.
You covered most of the option, Aman.
Yeah, thank you.
Okay, excellent. And we are a bit past the hour now, so we're going to wrap up here. For the audience, there should be a link to a survey on your screen. If you can just take a quick moment to answer that before closing out. And for us, we are going to close out today's webinar, but I definitely want to thank Juniper, Microsoft, as well as Bell Canada for joining and all of your insights today. So thank you, everybody.
Thank you.